showcase star. You can see here the VLT and KEK data suitably combined as far as they are public. In this plot, you can see 157 VLT data points and 38 KEK data points. So this is all the published work, and our latest data set is included here. And here's the spectroscopy. You can see that our latest data, that the star has been accelerating tremendously. I mean, each week the velocity changed by 40 kilometers per second. This plot contains 60 VLT data points, and I hope I counted correctly, 38 KEK data points. So let me come back on this, as how do you suitably combine it. The difficulty really is that there's a coordinate system issue, and there might be actually an offset, there might be a velocity offset, there might be an angle offset, there might be a rotational offset, there might be a scale offset, and many more effects you could think of. And this is the data, which is probably not the latest, because I can only access what was published in Berlin 2016. There you can see that apparently the KEK coordinate system here is moving with 0.4 or 0.5 milliarc second per year northward, but it was smaller. The latest numbers you have just shown, they were a bit smaller than that. So for the moment, I think we need to include those two effects to match the two coordinate systems, but I think I'm simply not sensitive enough to also check for the other effects, which could also be there. So what we get from this stellar orbit fitting is, of course, mass and distance to the black hole. You can see here our 2009, the latest published result before our update earlier this year. You can see how our statistical error bars have gone down simply by collecting more data and improving the analysis. And also, if you now include the bootstrap, you can see that now our statistical and the bootstrapping error together are smaller than our 2009 error bars. We do have a prior where we want to locate the mass. This comes from these SIO maser stars, which are infrared sources and radio stars at the same time. And Sag A star is a radio source. And with that, you can essentially check how well we can align. So you know the position of radio Sag A star. Then Mark Reed and team tells us where the position of the radio SIO masers are. Those you can also see in the infrared. And between those two things, you only need to correct for distortion. I say only because it's actually a lot of work. And there's of course, you have to assume that the maser spots in these stars trace the photocenter of the star. And then you can essentially look at where's the origin of your coordinate system in the infrared or the position of the flares from Sag A star. And you can compare that, and this is the test Andrea has been reporting. Here's what we are getting. So we also get that the position is on the order of 0.2 milliarc second in agreement in this test, and the velocity is on the order of 0.1 milliarc second per year. So this is our current level of agreement. However, you can also turn the question around, and you can ask the question, what position of the mass are actually compatible with the data still? So in that sense, you fix your mass position, and then you try to fit an orbit and ask how bad the chi-square is getting. And then you get actually quite a huge ellipse on sky where actually you could still accommodate for the mass. So that explains why the two data sets can be in let's say, apparent disagreement. If you plot them statistically, that is all fine. You can see this is an ellipse which has a few milliarc seconds across. So you've seen S2, and I would also like to introduce the second best star for us, which is S1. You can see here the astrometry and the radio velocity, and it's maybe interesting to think a bit about it. You can see the constraint from S1 there. It's extremely narrow ellipse, which essentially goes along third order parabola. And this is, if you think about it, if you only have astrometry, you only constrain a quantity which is m over distance cubed. So this parameter mu. And if you now measure astrometry and one radial velocity, this is essentially what you have. You see the radial velocity data is essentially one velocity. You get this mu constraint as before, but you cut off your distribution in R0. And this is why you get this limited ellipse. And you can see that this ellipse in mu dimension is actually better constrained for S1 than for S2, which is sort of surprising. It's not the mass, but the mu constraint is actually better for S1. S1 is sort of at an optimum radius how it constrains this parameter mu. It's maybe just a curiosity, doesn't tell you much. Currently, we on the order of 40 orbits are known, starting, of course, with the first detection Rainer has published and all the other papers. And so if you, the famous one is, of course, S2. And let me give you a bit of an inventory of the orbits. So in our data set, we see acceleration for 47 stars. We can determine 40 orbits, out of which 8 are disk stars. So that leaves us with 32 so-called S stars. However, of these stars, there are actually 30 which are young stars, and 8 are old stars. And for 2, we actually don't know it. So the classical S stars, which means young, bound orbit with interstellar disk, is only 22 stars. 17 of these stars are useful for determining the potential, and bound are 39 of the orbits. One orbit is actually unbound, so there's one star which is unbound to the black hole. So we have 17 stars which we can use for determining the potential, and if you think about this, it's actually a hard problem. It's a fitting problem which has 109 free parameters, so the error matrix has quite a number of entries. The number of data points goes in the thousands, and the parameters are degenerate with each other, and in particular they differ a lot by how much they contribute to the potential. And the way to express it is the condition number of your matrix, which is the ratio of the largest to the smallest eigenvalue, which turns out to be 10 to 10. And the numerical precision you need to invert a matrix is the square of that. So you would need a 20-digit thing, and this is why actually it's very hard to do a constrained orbit fit. And this is a problem I've been struggling with quite some time, and I'm very grateful to Reem, who has helped me in that. And what helps? Well, of course, we know a very good starting point because we have the S2 orbit, and we can fit all the stars individually in the S2 orbit to get good starting parameters. Also, we know that the stars don't influence each other, so for a given potential, you can minimize stars individually. And what is maybe the interesting thing is that for a given set of orbits, you can actually calculate 6 of the 7 parameters of the potential. You don't need to fit for them. You can calculate them when you have a set of orbits given. And so only the one parameter is free, which is this mu. And if you iterate those 2 last points, you're actually not strictly minimizing, but you're actually getting closer to the minimum. And what also helps is if you reparameterize things in terms of Thiele-Innes orbital elements. So it's a different way of representing the orbital elements. In the end, you get a multi-star fit, which has constraint, and you can see here the full data set and the astrometry and the radial velocities. The result of this fit is 8.3 kiloparsec. So it's this black error ellipse, which is drawn on top. S2 only is the bluish one, and the 2009 data is the larger one, which you can see going beyond the plot. The shaded contours below from the cluster parallax, which Sotiris Chatsopoulos was deriving in 2015. If I overplot the Böhle 2016 data, you can see that Keck and VLT actually disagree. And what I just did a minute ago is I tried to overplot your latest ellipse, Andrea. I hope I captured it right. So you see things have improved a bit. But there is a disagreement at the 2 sigma level. And here's a comparison of the distance estimates which have been published over time. Maybe worth pointing out the high mass star forming regions in the Milky Way, the cluster parallax, and then the 2 latest orbit measurements as published. But as Andrea said, her latest value was 8.1, right? It was not 7.9 anymore. Okay, it's clear that in 2018 we will detect the gravitational redshift. Here it's May 14 is for us the prediction, so we agree, I would say, with even almost on the statistical level. What is maybe worth to point out is that there's always a Keplerian orbit which looks like your relativistic orbit, and this is the biggest nuisance you have. And you have to determine your orbital element. So the Keplerian part of your orbit is this line here, but there's a better fitting Keplerian orbit to the relativistic data. For S2, we have actually integrated for many, many years, and the total integration time now exceeds 100 hours. So we have probably one of the best B-star spectra at all. You can see here the beautiful K-band spectrum, which essentially is noiselets, and in H-band you can see also all the bracket lines. There's a few stars which happen to be inside that field of view, and so you can do the same game for all those stars. You can see here S2, S4, S6, S7, 8, 9, S1, and S12. These are the stars for which you get this deep spectra. And what you learn from these spectra is that you can, via atmosphere modeling, determine or get an estimate on the surface gravity and temperature of these objects. The surface gravity, of course, is related to the radius. And with that, you can then compare to stellar evolution tracks, and you get out mass and age constraints, for example. And what one concludes from this analysis is that the typical age of these stars is rather on the young side. So they are not at the typical age for a B star, but they are rather only a few million years old, as you can see from this plot. Okay, Not all the objects are stars, so you can see K and an L-band image, and let me briefly comment on G2. So if you have a gas cloud which is falling towards a black hole on such an orbit, it cannot survive. That's obvious. And in the following, I would like to show you position velocity diagrams, which are cuts through these three-dimensional data cubes. But we don't make a straight cut, but we cut along the orbit. However, it's not a problem to have this predetermined orbit, because you're not cutting along a single pixel, but you actually cut something which is 4 pixels wide. So any uncertainty of the orbit you have is included in that. And in the following, you will now see a few plots of this type. On the left is always the data of this position velocity diagram, where position goes to the right, velocity from minus 4,000 to plus 4,000 kilometers per second is on the y-axis. And the middle plot, you can see that particular simulation I've just shown before. It's not because I think it's particularly correct, but because it's so simple, and that I can capture the basic features of the evolution by that simple model. That is my point. And in the right plot, you can see the on-sky projection of that same simulation. So this is how that looks on sky to you. 2004, 2006, 2008, 2010. And here it's maybe worth to stop for a second, because now you can see that in the data, the ellipse is actually tilted. And that means that the front side of the object is moving at a higher velocity than the back side. If you think about that, and if you think about a train running along a track, it's an unhealthy situation for the train. The train should not do that, the front side. It means the thing is tidal interaction. The tilt in this diagram is the tidal interaction. 2011, 2012, and in 2013, you can see that the first gas is going on to the other side. 2014, it was pericenter, so it's roughly equal. 2015, 2016, and unpublished 2017. So you see beautifully how such a simple model, I'm only using a few hundred test particles here and the Keplerian orbit, and that's all what you need. So you can ask, what have you learned? And for that, I need to introduce a game to you, which maybe in the US is not as well known as in Europe. It's soccer, and there's, there's penalty shots. And imagine you're a supporter of the blue team, and you drive your car, and you hear on the radio that you get this penalty shot. You're extremely happy. However, you're much more happy if you're sitting in front of a TV or in the stadium actually and allowed to see how this is happening. And there's a big difference in knowing that something is happening and actually see it happen. And so that's, of course, why astronomers get excited to observe obvious things. But sometimes it's actually important to see how things are happening. Look at this way. And that is actually valid. So the key actually is how you do it. It's not that you do it. So, and what is that for us? That is, for us, is the interaction with the accretion flow. So so far I've only shown a test particle simulation. The question is if there's any interaction with the accretion flow. And what we have been published this year is a simulation which uses test particles and a drag force. And then we fit actually the 3D data cubes. So we evolved this cloud in 3D and fit to the 3D data. So there's no selection effect of any orbit whatsoever. But we can only show then 2D slices, of course. So we can show, again, position velocity diagrams, or you can see here the same with velocity gradients derived. And what you get from that is essentially a limit. How much gas can there be? And you can see here in this particular plot that the density is on the order of 1,000 particles per cubic centimeter, which is lower than what a standard drive model would have given us. So, so far so good. There's more one can say, and this is work which from Elad Steinberg, who is supervised by Rehm. He was simulating that process at high enough resolution, and what he found is that actually this constant bracket gamma evolution is understandable, and it even gives you an upper limit on the Rives density. So the simulation they've set up is essentially a cigar of G2. You can see that thing there going through pericenter. It looks like what you've seen in the movie before. But with that, you can essentially mimic the constant bracket gamma luminosity, as long as your density is not too high. And what is actually the result of that is that the density should be below that number here. So you get something which is consistent. And finally, let me mumble a bit. So you can see here the Keplerian fit to the orbit in radial velocity, but you can also see a drag force fit, which does a better job in the 2015 and 2016 data. You can see that. It's doing slightly better. It's not statistically significant. However, in 2018, that might become statistically significant. So you do get a fit result for the density again. And the fit result is that purple line here. So again, you can see we are in around 1,000 or 2,000 particles per cubic centimeter is the density here. So let me sum up. I think it's clear that G2 has a gaseous component that can be used as a probe for the accretion flow. And this is completely regardless of what your source model is. It's actually useful. You can discuss for ages what you do with it, but it's useful. The S stars are probably a young specimen, so we might need to rethink the origin and randomization of the orbits in particular, because that was using longer timescales. And S2 continues to be an excellent probe. Stellar orbits are getting ever better, but this is a very hard argument. If you go to a telescope allocation committee, that's it gets very, very slowly better. But of course, we have the advantage that next year the relativistic effects are coming. And to really sum up, let me put up a picture of the VLT. The Galactic Center science, I think, is really driven by observations. It's one of these fields where observational progress really is pushing the field, particular adaptive optics. And on our side, integral field spectroscopy has been really tremendously rich. And of course, we profit a lot from the uniqueness of the VLT. It's ideally located on the southern hemisphere, and it actually consists of 4 telescopes. But this is a talk I'm not giving. Frank will talk about the aspect of using 4 telescopes to observe the Galactic Center. Thanks a lot for your attention. Yes. Mm-hmm.
How many kinematic measurements do you have for this?
It's the star, which is called, is it S111? So it's actually bright. It's 14th magnitude. It's a late type star. So the spectroscopy is fairly easy. We have many red velocities for that star as well. And the eccentricity is 1.05 or something like that, with an error bar of 0.015. So it's a 3 to 4 sigma, but it's consistently. I think it's the same star which also in the 2009 paper already was in. There was one which was formerly unbound, and this has, the error bar has gone a bit smaller, and it continues to be unbound.
We're both asking, it's a question. Would a binary component have done that?
I haven't thought about that, but the question suggests that the answer is yes.
So 700 kilometers per second?
At least, yeah.
Yeah, it's a few hundred kilometers per second. Yeah.
Do you remember how much is the astrometric?
True.
How much is
That's true.
The velocity?
Yeah.
Not out of my head, sorry.
So if you assume that there's a star mass black hole cusp in the galactic center near the supermassive black hole, is it possible to constrain its mass or mass distribution using the 17 stars?
In principle, yes. But let's say still 70% of the information from the potential comes from S2 alone. All the other stars add another 30%. And so it doesn't help that much yet to have all the other stars. But I think the limits are on the 2% level or something like that. But this is mostly given by S2 only. Also, I'm not sure if the effect would be an overall drifting of the orbital elements, or whether you would be dominated by individual events that all of a sudden one star makes something crazy which you wouldn't expect. What is the dominant effect? I actually don't know that. It's actually maybe something one could simulate what the observational effect of such a cluster would be. In the long term, it's clear that the orbits precess, but how would it look on a short time scale? I'm not sure.
Yes, just a short question on Stefan. When you show this nice drag force fitting, so you assume that the black hole have a, let's say, gaseous envelope which is spherical, or
Yes.
spherical?
It's a spherical Riev with the density profile 1 over R. The most simple thing. I mean, I'm a simple-minded observer, so.
Because the picture was slightly different. So the picture was a nice galactic disk kind of structure. So I'm just wondering if it's not a spherical
Yeah.
distribution, but more disky or flattened, which kind of
Well,
different effect you can have. So the density is probably also
yeah.
can be different.
Well,
yes?
that is some.
One more parameter.
Actually, Anne-Marie Madigan has worked on that. She used the fact that you can fit even a bit better if you look into the, let's say, the effect that the force is not in the direction of motion,
Yeah.
but a bit differently, and that gives constraints on the rotation of the accretion flow or
Yeah,
things like that.
Okay.
Yes. Stefan, in the 17 star feed that you performed, if you can go back to that, because you showed it as just for 10 seconds, but there appeared to be like a star that was like completely off as a feed from the data. And I was, like the green one in the middle. Does it tell you something, right, about your systematics? Like you see the feed from the bottom.
What? Is it an S4 or which one? S4?
Well, there is one that is clearly off. All the points are just off.
Which one? The right side.
No, that of the right side. Right, no, right, the right clock. The right clock.
Right.
Yes. One up, up, left, up, left, down.
Just tell me color. Which color?
Green, down, down,
Dark
dark green.
Dark
Dark
green.
green. Yeah, yes.
Uh-huh.
So is it like, does it tell you something about systematic, possible
No,
systematics,
I
or it's just?
would think it tells you about your systematics, not about astrophysics.
Yeah, sure.
Oh yeah, we're
So-
definitely all dominated by systematic areas,
I
right?
guess you must be
But
getting
this-
very similar
But
things.
this
that-
dark
SO8.
S, which one? S31 or what? No, this is not S31.
It looks like
This
it.
is
It looks like
Yeah, yeah, yeah.
18.
SO8 is this one.
18.
Yeah, yeah. 18.
SO8 is, what is SO8 in?
So I think that star must be SO8, right?
Right,
That's
SO8 is
SO8.
S31, right? That is,
It's the
No,
one
the
coming
one
from the
that's
top,
in
right?
the
Green
green.
one is,
Uh-huh.
I think in ours SO8. And what happened was that it was like it's like 3 stars for many years,
right.
and then it split apart in like 2006 or something, right? And so astrometry for that one we find heavily biased.
Yeah.
That's why
But
we
also
don't
the radial velocity for that star is biased because the velocity is close to the gaseous velocity at that point. So that is a particularly. So the goal of this exercise was to use as many stars as possible.
Sure, yeah.
Because if I go back and want to have as clean a probe as possible, I'm left with S2. So that was the other extreme, so to say.
Yeah, I was just wondering if something that you can learn about your bias is quite different.
Yeah.
But that there are stars that you're unable to feed.
Yuri.
So the fact that these S stars are all the same age as the Ds gives us, of course, fantastic image for scenarios where the origin of these stars is associated with flowers. But I'm just wondering how secure is this conclusion? Like the stellar models, how do they calibrate them in any reliable way?
Well, I suppose there are big systematics. This is the error bars reported are statistical errors, of course. And if you change the stellar models a bit, you might end up with different answers. This was Mayan did this work, and she concluded that this is the most likely fit. I think I would be happy to see an independent evidence of that type, because it makes really a difference in terms of the formation scenario, right? Because the randomization processes would need to be even faster than that.
Okay, let's think. Stefan again. I think he would use this one. Seems to be connecting. Yes. Should we have this for recording? Can I show you a sign 10 minutes before? Should not play with it.
Sure, give me any sign you want.
Okay, so our last speaker of this session is Andreas Eckart, again about the motion of stars in the galactic region.
Yes, and in particular about the 3 central stars, and I will do my very best to add more to the confusion. Of course, I don't have to give a big introduction. You know the region now well. It was introduced by the previous speakers. But I will give you an outlook through which I would lead you here. I will talk about the mass and the distance, how we derived it for S2, and what kind of data we actually used. And also I will then introduce a new practical method, how to derive GR parameters from orbits. And I will then use simulated stars, and we will derive a possible parameterization of getting the GR effects. And then in the end, I will try to apply this to S2. And all of this is mainly Mazia Paza's work, who unfortunately didn't come, but there is sprinkles of other contributions in here as well. So the data that we're using is the VLT data. It's our own observations plus archival data. So it's basically the same data that Stefan talked about, and also published Keck data, radial velocities, and so on. Then we went through the usual spiel of combining data and reducing data. So we flat fielded, sky subject, bad pixel corrected, and so on. And then we also combined the 13 milliarc second and 27 milliarc second pixel data that we have. And we restricted ourselves actually, just to be sure what we were doing, in particular for the registration, to data, to images where Sagittarius star was flaring as well. So we always would see Sagittarius star and the other stars. And then, as we said, as I said, we constrained ourselves to the three central stars, S2, S38, and S55 or S0102. Then the registration itself is, well, of the order of a milliarc second or 1.5 milliarc seconds for a single position. So we used the Mesa star coordinates as well, as far as they were available to us. And as I said, we constrained ourselves to data that has only Sagittarius star flaring. Then the overall data linkage coordinate problematic that was also addressed. We, of course, were aware of that as well and looked into it. So we basically combined the VLT and the Keck data by simple scaling and shifting, and checked against rotation by using the overlap in S38 data, because that has a larger distance from Sagittarius star, shows probably less GR effects. So we can use that to clinch on and to avoid to a certain but very precise level that the two data sets are rotated against each other. So that all seems to work rather well. Then the models we applied, we used the Einstein-Infeld-Hoffmann equation to model the motion of the stars. And that collapses, that includes the motion, the drift motion of Sagittarius star, both in r and in velocity. And it collapses if you say Sagittarius star is compact, and then it boils down to the formula that we used already in Rubilar and Eckert in 2001. So this is how it looks like. These are the orbits of the three stars. Here we plot only the data that we input into the system ourselves. But as I said, on the right-hand side, you can see that we used Keck positions that were published by Böhle et al. And also radial velocities by Gillison and Böhle. So we used everything that we could actually combine. Then we did MCMC models, fits, both relativistically and non-relativistically, and came up with estimates of the mass and radius. And those numbers that we get here are consistent with what everybody else gets as well. So we're not too bad. The S2 periaps question we addressed as well. We find middle of the year, and that's how it goes. So the relativistic orbits of stars and general relativistic effects. So there's a few phenomena that have to be taken into account. There's basically the low order effects like redshift, and that were addressed earlier, and then also effects on the long axis and on the ellipticity of the orbit that will change during the orbital phase. Yeah, well, but you will also have a larger error. So I think the orbital elements are sufficiently unsecured to make a very, very firm statement. But that depends on the amount of accuracy that you think your data has. So I think we are in agreement, but you may be right with your fine statement. That's okay. Higher order effects we did not look into, like frame dragging or gravitational lensing. And one has to point out there's three major contributions to the periaps rotation. There's the periapse rotation within the plane, that's prograde or retrograde, depending whether it's relativistic or Newtonian. And there's also the problem of the dark mass that is surrounding such a star, possibly. There can be up to 10 to the 4 solar masses, 10 to the 4 solar masses in the form of whatever, black holes or something like that. And that can have some graininess. And that means the stars move in and out of the orbit. That means the potential on that level changes. And that can move your orbital plane back and forth a little bit. So that needs to be taken into account. We didn't do that in the FITs. I will say something at the end concerning that problem. So this is now the overview of the stars that were available. Basically, what we didn't use are the S stars here, the red ones on top. We just used the yellow ones, the 3 innermost. And these are the simulated stars. Here plotted in 1 minus E and periapse distance against the long axis. And what you see is that we try to get simulated stars well within the radii of the 3 closest stars, but we had to stop, of course, at the innermost radius at about 0.1 milliarcseconds. That is where stars would not survive and would be disrupted. So we covered basically the whole phase space with simulated stars. And those are plotted here again, the long axis and the eccentricity against a relativistic parameter that we choose. And in both plots, E and A are parameters here as well. The relativistic parameter was introduced by Zucker et al. And that is the ratio between the Schwarzschild radius and the periapse distance. Now, there's many relativistic parameters that you can think of, but that one in particular has the advantage that it is linked to things that can easily be measured, more or less, or inferred, and that is proportional to delta omega, that is the periapse rotation. Now, the method. Stefan pointed out that, in fact, you can fit any ellipse to the data and camouflage the relativistic effects. There's always a best ellipse that you can fit. So that is not the way to go. You have to be more inventive here. So on the left-hand side, you have the non-relativistic case. It's easy, few orbital elements, negligible computing time. It's quick. On the right-hand side, you have where the problems are born. It's a relativistic orbit. You need to have a central mass. Depending on whether you do it in a plane or inclined, you need to have 5 to 7 launching points for your star. You need to use the post-Newtonian formalism, which is an approximation. And you use to get something, a Runge-Kutta method or something like that to get your orbits. And that is rather temperamental. So you have to make sure that in the non-relativistic case, your orbits are always closed. And then you can switch on relativity and look at the result. So that makes a lot of headache. And that has also involves non-negligible computing time. So, but in any effect, the relativistic orbits can now easily be parameterized. And we need to find a simpler method to describe the relativistic character of an orbit, and preferable by simple non-relativistic orbit fitting, because that's quick, combined with suitable parameterization. To do that, we introduced the method of squeeze states. That is, you have the product of 2 quantities which are limited by a small number, epsilon here. And if you choose alpha and beta as your fitting or your goodness parameters, like e to the minus chi square, then you can write it like this in the second line. And what we do here is actually we take into account the modification of the orbital shape due to relativity. That is, we fit the lower and the upper part of the orbit separately. And the lower and the upper part then also can be subdivided into a systematic misfit due to the fact that the lower and upper part now don't belong to an ellipse, but to a Rosetta-shaped orbit, and to a random part, of course, that's due to noise. Alpha and beta are just 2 quantities. Yeah, think of it. Think of it as the uncertainty principle, right? This is delta x and delta p. So if you get one exact, the error moves to the other, right? You will see now in this graph. This explains what we mean. So here we have the dashed line is a Rosetta-shaped orbit, and the 2 colored lines, the red one and the blue one, are fits to the upper part and the lower part of the orbit. So if you fit the upper part nicely, yeah, the lower part is messed up, and vice versa. So you basically squeeze the uncertainties of the orbital fitting to one side by fitting the other much better. So doing that, then you can define yourself a ratio that is, for instance, the fit of the general fit of the upper side divided by the better fit of the upper side if the lower side, or by the worst fit of the upper side if the fit to the lower side is optimum. So in how far your fitting quantity deteriorates by just constraining yourself to one side is a fit, is a measure of relativity, is a measure of the misfit between the ellipse and the Rosetta-shaped section. And that actually can be parameterized with a relativistic parameter. So you see the ratio is 1 if it doesn't matter, if you have an ellipse, yeah, and the relativity effects are very, very small. And the ratio becomes much smaller if you go to a higher relativistic case. So that misfit parameter could be used, but actually we are using other quantities which behave similarly well. That is the change in the long axis of the different fits and the change in the ellipticities of the different fits to the lower and the upper orbit. And also you can also use delta omega, which is basically the same, but with with respect not to the upper and lower orbit, but to the left and right side, to the ascending and descending part of the orbit. So that's depicted here. So you have a delta E and delta A if you compare the lower and the upper part of the orbit, and you have a delta omega if you compare the ascending and descending part of the orbit. So all of these 4 quantities can be used to measure the misfit, i.e. the difference between ellipticity and a Rosetta-shaped source. So that has now been done with our simulated stars. Yeah, there we had the orbits at hand and could determine all these quantities. And here again you see the ratio of the A ratio, the lower fit to upper fit A ratio, A value ratio, and you see if it's non-relativistic, if you're close to an ellipse, that ratio is 1, and it decreases if you go to the relativistic domain. Similarly here, the ratio in ellipticities is 1, and then decreases if you go to relativistic orbits. So this is a very nice way to characterize the relativistic character of your trajectory. And here the same result for delta omega, which is proportional to the relativistic parameter that we introduced. Again, delta omega is 0 here in that case. If you're non-relativistic and becomes larger, the more you are relativistic. Now, question. Of course, we want to use this. Is the current single-dish AO data set for S2 accurate enough to show the effect of GR? The procedure is clear. You take the S2 orbital data, determine the A ratio and the E ratio and delta omega, and compare it to those graphs that we derived. So that's the result. So you have to squeeze yourself up into the corner where you're hardly relativistic. And you see that if you take the mean with the conservatively dialed through uncertainties through the whole system, then it looks rather insignificant. It looks more significant if you take the median. But as I said, this is for delta omega the same case, so you do see an effect. But as I said, the uncertainties have been dialed through the entire process, reference frame, uncertainty in positional fitting, and so on and so forth. But for S2, since we have used only data that contain Sagittarius A star flaring, we can restrict ourselves to the positional uncertainties in that case as well. And then we can, as we pointed out in the paper, we can, in the section 5.3, we can make a Gedanken experiment and assume that about 5 or 9 measurements fall on each orbital quarter and result in a displacement of that quarter. And then you can think about the possible combinations that you can have and find then by just thinking about it that there's a 3 to 4 sigma significance in that involved if you get all quantities, the A and the E ratios and the delta omega on the right side of the distribution. That has been quantified here now. So we take 7 data points, we use 1.5 milliarc seconds as an intrinsic uncertainty of the positional measurements, and then we are allowed to shift to the left, right, up and down, or just leave it each orbital quarter by about 0.5 milliarc seconds. And we can look at the distribution, and then we can determine these quantities. As you can see here, it has an effect, how you shift it has an effect on the ellipticity ratios and on the A ratios, or on the delta omega, depending on what you do. And these are distributions. For E and A, they're not that nicely Gaussian, but for omega, they're very nicely Gaussian. The 1 sigma point is indicated, and the measure of S2 is indicated as well. So if you judge on the significance of the measurement that we did with respect to a noise-dominated model, you find that the values we extracted are all outliers and indicate that there is a 3 to 4 sigma measurement here, or a certainty here. So that is a visualization of the effect. And as you can see, while the periastron shift is actually taking place while S2 is swinging around Sagittarius star, the effect of it with single dish telescopes can more easily be measured if you look at the entire orbit, because the long axis gives you a lever that increases the effect on the angle that the angle has, the angle delta omega has. So there's a difference in the orbital position that can actually be pinpointed the way I explained. So that led to a nice ESO press announcement, which everybody was able to look at. Now let's go to the graininess that needs to be mentioned. It needs to be taken care of, and it so happens that the number of bona fide black holes, as you could determine them in the X-ray domain, as X-ray sources, increases towards the center. And so there's quite a number of them. And in any way, the assumption is that a large number of remnants will sink to the bottom of the potential well. And if you assume 10 solar mass population of black holes that you wouldn't see, that could contribute to the dark matter, you would have that graininess effect. And it becomes more and more grainy the more mass you allow for your black holes to contain. And as we have shown in the paper Sapra in 2012, that effect can be substantial. So here we have taken 2,000 solar masses in 10 or 20 solar mass black holes, and it can actually contribute to the periapse motion. So what is shown here is for different cases, the periapse motion shift, and the GR effect has been taken out, the 11 minutes. And you can see that it can contribute significantly and even can go the other way, depending on what the distribution of masses is. So the graininess needs to be taken into account. However, if you look at the amounts, a few arc minutes, and the exactness, although I think significant, of our measurement, we can't make any statement about this, and higher significance is actually needed, or more precise measurements of the effects are needed to make a statement on the graininess of the dark matter around Sagittarius star. So as a result, we got a mass and a radius, a distance, which is in agreement with most other derivations. We have a periapse time, which has a large uncertainty, but which is also fine. So it tells you at least that it's going to be somewhere it's actually not July, I see here. Yeah, whatever. It's going to be in mid of next year. And we do have a measure of delta omega, and I think it has a 3 to 4 sigma exactness on it. So the uncertainty is probably rather 3 minutes than 7 minutes, as we got from just dialing the uncertainties through the system. And the expected value is 11, and we measure 14. And we can also determine the relativistic parameter. We would expect 0.00065. We measure 0.00088. And the uncertainty here is probably rather 0.0004, depending on how you actually do it. And summary. So we got mass and distance both with Newtonian and post-Newtonian solutions. We developed a new method to determine the degree of relativity from orbits. And we got a measure that is probably a 3 to 4 sigma event that indicates that the quantities, the relativity quantities, are of the order of what you would expect them to be. So if that is true, and if you accept that, then S2 would be the first star for which that could be done. And it can only get better. So we are all looking forward to more precise KEK and VLT data, and also to more and new VLT gravity results that probably Frank will allude to. Thank you very much.